Good morning students. In this lecture, let us discuss about ferromagnetic hysteresis and types of magnetic material. First, let us see what is hysteresis. Hysteresis is the property of a ferromagnetic material, which means lagging. So, the word hysteresis means laggings. So, lagging of magnetization behind the magnetizing field is known as hysteresis in a ferromagnetic material. When a ferromagnetic material is subjected to magnetization, which means the cycle of magnetization starting from 0 to a particular value of positive value and to a negative value. So, the magnetization will attain a cycle that is known as hysteresis. When the temperature of ferromagnetic substance is less than its Curie temperature, the substance exhibits this hysteresis behavior. The domain concept of a ferromagnetic material is explaining this phenomenon of hysteresis. The increase in the value of resultant magnetic moment of a ferromagnetic material under the action of the applied field can be attributed to the two processes. One is the motion of domain wall and the rotation of domains. So, look at this picture. The hysteresis loop of a ferromagnetic material. So, look at this this segment OC. So, here in x-axis the magnetic field is given, in y-axis the intensity of magnetization is taken. The magnetic field is increased, the magnetization is also increases up to the point A. So, in this region the magnetization is produced by the movement of the domain wall. So, up to this region, up to this OA region, the domain wall movement will be reversible. So, when we remove the magnetic field, it will come to the magnetization is also come to 0, so, which means the domain wall movement will be reversible in this region. So, beyond that, when we increase the magnetic field, the intensity of magnetization is also increases. So, at the point A to B, up to this region A to B, the movement of domain wall will happen, but the movement of domain wall is irreversible in this region. Up to in this A to B region, the movement of the domain wall is irreversible. So, beyond the point B, when we further increase the magnetic field, the magnetization is also gets increased, but this is occur due to the entire domain wall rotation. So, due to the rotation of domain wall beyond the point C, the magnetization is produced. Beyond the point, beyond this, when we increase the magnetic field, there is no magnetization will occur. So, the magnetization attained here is known as the saturation magnetization. So, beyond this, when we increase the applied field, there should not further increase in the magnetization. Look at this. When we decrease the magnetic field at this from this point A, it will not go to the O via this way. When we decrease the magnetic field to 0, the intensity of magnetization is decreased to the value B. So, this is known as the retentivity of the magnetic material. So, retentivity means it retains some magnetic magnetization when we completely remove the magnetic field. So, this is known as retentivity. So, retentivity is the amount of magnetic induction, which means this region OB. So, the amount of magnetic induction retained in a material, in this ferromagnetic material, after removing the magnetic field. So, this is known as retentivity. So, beyond this, we have to supply a reverse magnetic field in this direction. So, then only the magnetization will reaches to 0. So, when we further increase the reverse magnetic field, the magnetization will also increases in reverse direction and it reaches this point D. So, after this that um, if we increase the electric applied field, so it goes to the point A via this EF. So the cycle of magnetization versus magnetic field, the magnetic field versus magnetization curve that execute a cycle starting from the point O, it goes to a saturation magnetization A, and when the magnetic field is completely removed, it will not come to O, it will reach this point. So it retains some magnetic field, that is due to its retentivity. Here when we have to supply a reverse magnetic field to nullify this retained magnetic magnetization in a magnetic material. So beyond this C, so at this point, this is known as coercivity, the OC, the segment OC. So coercivity is the amount of magnetic field applied, this one OC. So the amount of magnetic field applied in the reverse direction to remove the residual magnetism completely. So to completely remove the magnetization occurred in a ferromagnetic material, the magnetic field is given in reverse direction. The amount of magnetic field OC is given in reverse direction. So this is known as coercivity. So beyond this, we further increase the reverse magnetic field, it will reach the point D. So beyond this point, we continuously increase the field, applied magnetic field, so it will reach the point A via this E, F and A. So this cycle is known as the hysteresis loop. So when we study about the hysteresis loop, we should know these parameters. So first, retentivity, the amount of magnetic induction retained in a magnetic material after the removal of magnetic field is known as the retentivity. This is also known as residual magnetization. Next one is coercivity or coercive force, which means the amount of magnetic field applied in reverse direction to remove the residual magnetism completely from the ferromagnetic material, that is known as the coercivity. Next one is hysteresis loss. When a specimen, which means a ferromagnetic material, is taken through a cycle of magnetization, then there is a loss of energy in the form of heat. This is known as hysteresis loss. And finally, the quantity energy product of a magnet, which means the energy product of a ferromagnet. The product of it is a product of retentivity and coercivity of a ferromagnetic material. This is simply written as the energy product. So energy product is nothing but it is the product of these two, retentivity and coercivity of a ferromagnetic material. Its product is known as the retentivity, so which represents the maximum energy that is stored in a ferromagnetic material. Next, hard and soft magnetic materials. Based on the hysteresis behavior, the ferromagnetic materials are classified into two types, which are hard and soft magnetic materials. The first, hard magnetic materials. The materials which cannot be easily magnetized or demagnetized are called as hard magnetic materials. The properties of hard magnetic materials. The area of the hysteresis loop of a hard magnetic materials is large. Look at this picture. So generally the hard magnetic materials have a hysteresis loop like this. So it has a hysteresis loop which has a large area. So this type of material cannot be easily magnetized, also it cannot be easily demagnetized. So the area of the hysteresis loop is large for the hard magnetic materials. So the hysteresis loss for this type of material is high. The coercivity and retentivity of the hard magnetic material is large. See, this is coercivity, retentivity, and this is coercivity. So, retentivity is almost equal to the saturation magnetization. So, once this type of material is magnetized, so we have to supply a large reverse magnetic field to demagnetize this type of material. Because of this type of material is used to make a permanent magnet. The permeability and susceptibility of hard magnetic materials are low. The eddy current loss for hard magnetic material is high. Examples of hard magnetic materials are aluminum, nickel, cobalt alloy, steel, hard ferrites or ceramic magnets, etc. The hard magnetic materials have a number of applications that includes automotive, telecommunication, data processing, consumer electronics, aerospace, surgical scanners, electronics and instrumentation, etc. The hard magnetic materials which are used for making permanent magnets, that is used in motors, dynamos, voltmeters, loudspeakers, ammeters and microphones. Next, soft magnetic materials. The magnetic materials which can be easily magnetized or demagnetized is called as soft magnetic materials. So, look at this picture. The soft magnetic material possess the hysteresis behavior like this. So, a small magnetic field is applied. So it is easily magnetized. So for the application of small magnetic field, it quickly magnetized. Also, by removing this, it is easily demagnetized. So this type of material is known as soft magnetic materials. So area of the hysteresis loop is small for soft magnetic materials. So the hysteresis loss for this type of material is small. The coercivity and retentivity of this type of material, soft magnetic material, is low. Permeability and susceptibility of a soft magnetic materials are high. Since this type of material can be magnetized or demagnetized easily, so this type of material can be used to make these type of materials are used to make electromagnets. Next, the eddy current loss of soft magnetic materials is low due to high resistivity. Examples of soft magnetic materials are iron silicon alloys, ferrous nickel alloy, pure iron, mu metals, etc. The soft magnetic materials are used in AC and DC applications. The soft magnetic materials are used in magnetic data storage devices for reading, writing and storage purposes, along with electric doorbells, relays, transformers, cores, etc. Thank you, students.